So imagine this really high-stakes scenario for a second. You have two critical services talking to each other in production.
Right, the classic distributed system setup.
Exactly. One is written in Python and the other is written in Java. The Python side is just, doing its thing, and it sends over a dictionary of data.
Okay.
And inside that dictionary, there's a key called price, and the value attached to it is a string. But over on the receiving end, the Java service is rigidly expecting a double, and it expects it to be called cost.
Oh, wow. Yeah, that is a classic, deeply painful mismatch.
It really is.
And, the truly terrifying part of this scenario isn't just that the data is wrong. It's the fact that nothing explicitly breaks when that payload is sent.
Right. There is no compiler error to save you here. The Python code runs totally fine.
Yeah, and the Java code compiles without a hitch.
And your test suite probably passes with flying colors, right? Because the Python tests mock out the Java side, and the Java tests just mock out the Python side.
Exactly. So the call happens across the network, it fails completely silently, and the Java service just uses a default value. Or maybe whatever garbage value happens to be in memory.
And nobody notices a thing until a customer is charged the completely wrong amount in production.
Or worse, critical financial data is just silently lost in the void.
It is the exact kind of bug that keeps engineers awake at night. And it happens fundamentally because there is no real contract between those two machines. Protocol buffers, or protobuf as it's usually called, is Google's solution to this precise nightmare.
Yeah, they built this entire language purely because service-to-service data mismatches are so incredibly common.
And so wildly expensive to fix after the fact. So our mission in this deep dive into Chapter 2 of the sources is to understand exactly how protobuf creates an ironclad data contract, ensuring a silent failure like that just never happens to you.
Okay, let's unpack this. What does this contract actually look like in practice?
Well, the foundation of this contract is actually surprisingly simple. It is a single plain text file with a .proto extension. Just a text file.
Just a text file. But that file becomes the absolute undisputed single source of truth for both services. So to prevent the silent failures we just talked about, both the Python sender and the Java receiver point to this exact same file.
Ah, got it. So all the ambiguity about, what a price is or what a cost is, that gets completely removed.
Precisely.
So there's no more guessing, no more relying on some stale wiki page that says, hey, we think the billing service returns a string here.
None of that. It's codified. And inside that .proto file, the core building block you're going to use is called a message.
Okay, a message. For you writing Python and Java, think of a protobuf message exactly like a Python data class or a Java class that only contains fields.
Right, no methods.
Exactly. It doesn't have behavior attached to it. It is purely a structured container for your data. Let's make this concrete. Say you are building a backend for a bookstore, and you need a standard way to describe what a book looks like across all your microservices.
So you would open your file and define a message called book. And inside that message, you list its fields.
Simple enough.
But unlike a regular class definition in Python or Java, every single field in a protobuf message strictly requires three things: a type, a name, and a number.
Okay, let's start with the type. You have your book message, and you need to tell Java and Python what the data actually is. Now, protobuf has 15 scalar types available.
Yeah, quite a few.
But you really don't need to memorize all of them today. The daily drivers, the ones you will use most often, are string for text, int32 and int64 for your integers, double for floating point numbers, bool for true or false, and bytes for raw binary data.
And it is worth briefly noting there are variants for specific use cases.
Yeah.
You have unsigned integers like int32, signed variants like signed int32, fixed width variants, and a standard float.
Right, but those first 6 really do cover the vast majority of real-world fields you will ever define.
They absolutely do.
And having that explicit type is huge. Think about the bridge we are building here. Python is dynamically typed, right? It's perfectly happy to let a variable be an integer 1 second and a string the next.
Oh yeah, doesn't care.
But Java is statically typed. It needs to know exactly how much memory to allocate up front. By forcing both sides to agree on, say, an int32 for the page count, we bridge that gap perfectly.
Exactly. The Java side allocates the right memory, and the Python side knows the constraints before it ever sends a single byte.
Awesome. So once you establish that type, you need the name. This part is pretty straightforward. It's just what you, the developer, call the field. So title, author, price.
Right. You will use these exact names when you are writing your business logic and accessing the fields in your actual Python or Java code.
So we have the type and we have a name, but then there's the third requirement for every field, which is the number. And this is where protobuf really diverges from what we are used to seeing in a standard class definition.
Yeah. What's fascinating here is that the names like title or price are strictly for you, the human developer. The numbers, however, are for the machine.
Okay, how does that work?
Every field inside your book message gets a unique integer assigned to it. So title is 1, author is 2, price is 3.
So if the names are just for the developers, the machine must use those numbers to map the data. Does that mean the strings themselves, the actual words we type out to name our fields, are completely dropped when the data's sent?
You nailed it. They never cross the network.
Oh, wow.
When the data is serialized and sent over the wire, the bytes do not contain the field name title. They only contain the field number 1, followed directly by the value.
That is incredible. Think of it like ordering at a massive, really busy fast food restaurant. You don't stand at the counter and scream, "I would like the double cheeseburger with extra pickles, a large fry, and a Diet Cola," over all the noise.
Right, you just say, I'll take a number 3.
Exactly. Protobuf is doing the exact same thing for your network. It's swapping a long, expensive string for a really cheap 1-byte integer.
It is a massive optimization. You aren't constantly sending the word author over and over again for every single book in a massive catalog. And this design decision is the primary reason protobuf is so incredibly compact.
Especially now in March 2026, when systems are scaling faster than ever and cloud egress costs are just through the roof, that kind of efficiency is non-negotiable.
It really is. You are saving massive amounts of bandwidth.
Yeah.
And beyond the bandwidth, that number system enables incredible backwards compatibility.
Oh, really? How so?
Well, because the receiving machine only cares about the number, you can easily add new fields to your messages later. Say, giving the book an int32 field called publication year and assigning it number 4.
Okay.
Older clients that haven't been updated yet will see field number 4, realize they don't know what it is, and just safely ignore it without crashing.
Ugh, that is so clean. Okay, so putting it all together for our bookstore, we open our Proto file. We write message book. Inside, we define a string field called title, assign the number 1. A string field called author, assign number 2. A double field called price, assign number 3. That right there is our solid data contract.
It is elegant in its simplicity, but a real-world system rarely relies on just a single isolated message.
Right.
The true power of this contract comes from composition. Messages can reference other messages as field types.
Oh, just like objects referencing other objects in Java or Python.
Precisely. You wouldn't just have a book. You would define a customer message containing a string for their name, a string for their email, and maybe an int64 for their account ID.
Makes sense.
Then you can define an order message. And inside that order message, you have a field whose type is customer, and another field that is a list of your book messages.
So you are building complex, highly structured systems using the exact same object composition skills you already use every day. Okay, so we have these complex nested messages living in our plain text file. But how do we organize them? Like if I have a massive microservice architecture, how do I prevent the inventory team's book message from colliding with the billing team's book message? Because they might need totally different fields.
That is a great point, and it brings us to the syntax and organization of the file itself. Every .proto file starts with a syntax declaration at the very top.
Right.
And the version you're going to see in most code bases today is Proto3. It is the modern standard.
Yeah, the sources mention Proto3 coexists beautifully with the newer protobuf editions, specifically edition 2023. So starting with Proto3 doesn't lock you into outdated tech at all.
It doesn't at all. They interoperate seamlessly. So once you declare your syntax at the top of the file, you organize your messages using the package keyword. This is how you prevent those naming collisions between the inventory team and the billing team.
Ah, okay. So if you are writing Java, think of the package keyword in protobuf exactly like Java packages. If you are writing C++B, think of it like namespaces. It just logically stokes your messages.
Yes.
Though, as a quick heads up for you Python developers out there, the protobuf compiler actually ignores the package directive in Python, since Python relies on its own module directory structure.
Right. That's a good distinction to make.
But you still absolutely need to use it in the .proto file to keep the global contract clean and to keep the Java side happy.
Yes, it is a critical best practice to always namespace your files. But as we get deeper into Proto3 syntax, we have to talk about a hidden gotcha.
Oh boy.
Yeah, something that trips up almost everyone when they first start using protobuf, especially if they are coming from a REST and JSON background.
I think I know where you're going with this.
The default value behavior. In Proto3, every single scalar field has a default value when it is not explicitly set by the sender.
Okay.
For strings, the default is an empty string. For booleans, it's false. And for all numbers.
Wait, hold on. Interrupting you there. The default for numbers is 0.
Yes.
Hold on. If the price field on my book message defaults to 0, how do I know if the book is actually free? Or if the API sender's code just broke and they forgot to include the price field entirely?
You don't. That is the trap. Under standard Proto3 rules, you literally cannot tell the difference between a field that was intentionally set to 0 and a field that was just entirely missing from the payload.
That feels dangerous. If I'm a Python developer used to checking if a dictionary key is none, or a Java developer checking for null to see if data is missing, this is a massive paradigm shift.
It is.
Why would Google design it this way? It seems like it invites the exact kind of bugs we are trying to avoid.
It is a very common reaction to feel that way, but it helps to understand the mechanism behind the decision. In earlier versions of protobuf, specifically Proto3, the machine had to maintain a hidden bit mask.
A bit mask?
Yeah, essentially a little checklist attached to every single message, just to track whether a field was explicitly provided by the sender or if it was just empty.
So if a message had 50 fields, the system had to manage this extra checklist just to keep track of the nulls.
Exactly. And checking that checklist for millions of messages ate up valuable CPU cycles and memory. Google realized that for the vast majority of use cases at their massive scale, they didn't actually need to distinguish between missing and 0.
Wow, okay.
So by enforcing a universal default of 0, empty string, or false, they drop that bit mask entirely. The parsing logic becomes blazingly fast, and the generated code is much simpler.
But what if I really truly need to know if the sender explicitly set the price to 0 versus just forgetting it? I mean, what if that distinction is critical to my business logic?
There are workarounds. Google eventually introduced the optional keyword for exactly this scenario, which essentially brings back that presence tracking bit mask capability for specific fields.
Okay, that's a relief.
Yeah, we will be exploring how to use optional properly later in the series. But for now, you just need to be acutely aware that if you ask a standard Proto3 message for a number it doesn't have, it will confidently hand you a 0.
That trap. You know, getting a 0 when you expect a missing field might make some listeners think, why am I putting up with this?
Right.
JSON wouldn't do this to me. JSON has nulls. JSON is easy. Every single language has a library for it out of the box.
Okay.
So what does this all mean for JSON? If protobuf requires learning a new syntax and dealing with default value traps, why go through the trouble?
It all comes back to the fundamental trade-off between human convenience and machine efficiency. JSON is wonderful for humans. We can read it instantly.
Yeah.
But as strict contract between machines, it is incredibly weak. JSON has no built-in schema.
Which brings us right back to the catastrophic production bug we opened the show with. JSON doesn't enforce that cost as a double. It just holds whatever you put in it.
Right. Furthermore, think about the network overhead using our bookstore example. We established that protobuf drops the field names and only sends the field numbers.
I'll take a number 3 instead of asking for a price.
Exactly. JSON does the exact opposite. It repeats the field names in every single message.
Oh, I see where this is going. If I want to send an array of 10,000 book objects in JSON,
You are transmitting the literal string page count 10,000 times over the network.
that is a staggering amount of wasted bandwidth when you really picture the bytes going across the wire.
It is. And it's not just the network bandwidth, it is the CPU overhead of parsing that text. This is a critical distinction. When a machine receives a JSON payload, parsing that text is fundamentally a computationally heavy process.
Let's break that down. Why is text parsing so heavy for a CPU compared to binary?
Because the CPU has to read through the JSON payload, essentially character by character. It has to load the characters into memory, scan forward to figure out where the curly braces open and close, check for quotation marks, look for the colon that separates the key from the value, and then algorithmically parse those text characters into actual integers in memory.
That sounds exhausting.
It is doing a massive amount of matching and validating.
Whereas with protobuf,
With protobuf, the payload is already binary. The CPU reads a tiny integer tag, our field number, and that tag tells the machine exactly what type is coming next and exactly how many bytes to jump ahead.
So there is no scanning for quotes or colons.
None. The CPU just leaps through the memory, placing the data exactly where it belongs. It is orders of magnitude faster.
So the core philosophy here is that protobuf deliberately trades the human readability of the raw serialized bytes in exchange for a strict, unbreakable schema, incredibly compact network size, and blazing fast CPU parsing.
Yes. And it's vital to remember you can still easily read the .proto contract file. It's just plain text. It reads just like code. You just can't read the raw network bytes flying between the servers without a decoding tool. And when back-end machines are the ones doing the talking at massive scale, that is a trade-off absolutely worth making.
It makes total sense when you put it like that. Let's do a quick recap of our mission today. We established that protocol buffers serve as the ultimate data contract.
Yes, they do.
By defining your data in a .proto file, both the Python and Java sides know exactly what the data looks like, what types to expect, and they share a single source of truth that can be version controlled right alongside your code.
Exactly.
We explored how field numbers replace names to save bandwidth, how messages can be composed together, and why Proto3 uses default values to keep parsing fast.
But as powerful as that .proto file is, right now, it's just a description. A plain text file doesn't actually run or execute in your application.
Exactly. We have really only scratched the surface. In the upcoming chapters, we will explore even richer types, things like enums, nested messages, and repeated fields to handle lists and arrays.
Which are crucial for real applications.
And then we will dive into the real magic, using the protobuf compiler, known as Proto, to take that plain text file and actually generate runnable native Python and Java code that you can import directly into your projects.
That is where the theoretical contract becomes a physical reality in your code base.
I can't wait to get into that. But before we wrap up, I want to leave you with a final thought, something to chew on before our next deep dive.
Okay.
We've talked all about how this .proto file creates perfect harmony between different services. But think about the human element. If your entire back-end architecture across all the Python teams and the Java teams now depends on this single plain text file to communicate who in your organization actually owns that file.
Well, that's a great question. Is it the team sending the data, the team receiving it?
Or does this strict data contract require a completely new way of collaborating across your engineering department? Give that some thought. We'll see you next time.